Hello, this next video covers section 2.4, which goes over arc length of a curve and the concept of finding surface area. And we'll do two videos for this section. The first video will cover arc length, which has many real-world applications. For example, one which is talked about here in the introduction might be that if a rocket is launched along a parabolic path, we could use arc length to find how far the rocket travels. And then at the end, in the second video, we're going to talk about finding the surface area of a solid of revolution. So let's jump in and look at arc length. So before we do an example, I want to really quickly go over develop how this concept works. And we're going to kind of use an approach similar to what we used in Calculus 1 when we talked about finding the area under a curve, or even the section 2.1 from this chapter where we talked about finding the area between two curves. So we're going to have a curve, you can see here in figure 2.37, and just like in Calc 1 and this class 2, we're going to think about taking this interval that goes from A to B, and we're going to break it up into a bunch of subintervals. And so you can see right here, this one in particular is broken up into 5 subintervals. But if we were to zoom in on one of those subintervals, we have here in figure 2.3i8 what that might look like. And if it starts at xi minus 1, this subinterval, and ends at xi, then we have this small portion of the curve, and you can see here in orange there is a secant line that's drawn between the two endpoints. So the first thing we're going to do is we're going to think about finding what this distance, the length of this secant line is going to be. So if we call that distance there, that orange secant line, if we call that d, we know that by the Pythagorean theorem that d squared would be equal to delta x squared plus delta yi squared. Hopefully you all agree with me on that. And of course, again, this is by the Pythagorean theorem. So let's go ahead and state that. This is the Pythagorean theorem. And then, of course, we could take the square root of both sides, and if we took the square root of both sides, we would get that d is equal to the square root of what we have on the left side, or on the right side, excuse me. So we have delta x squared plus delta yi squared. And that, of course, that result is our distance formula that you've probably seen before in other classes. This is the distance formula. And what we want to do is use a little bit of calculus to kind of change the formula for this distance equation you see right here. So you may or may not recall from Calculus 1 the mean value theorem, but let's go ahead and review that. So if we look at the mean value theorem, the mean value theorem says the following. Mean value theorem says that there has to exist some point, let's call it x star, so some x star in our subinterval here. So remember, our subinterval goes from xi minus 1 to xi. So there exists some x star in that interval such that the derivative at that point, so we call that f prime of x star, is equal to the slope of the secant line. So, and of course the slope of the secant line, that would be rise over run, so that would be delta yi over delta x. That's what the mean value theorem says. It says that, in other words, there has to be some point call it x star, such that the slope at that point is the same as the slope of this secant line that has a distance d, or a length d, which should make sense. Now, of course, there's some other wording in there, like it has to be continuous. And of course, this curve is continuous. And whenever we're doing arc length, we will have a continuous curve over the interval. So, but what's useful about this is then we can rewrite this expression that we just developed here using the mean value theorem, because we can clearly see then that delta yi is equivalent to f prime of x star times delta x. And that allows us to rewrite our distance formula, because we can then take this and we can plug it in here, and that allows us to have everything in terms of x, because right now this distance formula has x and y, but we want to have everything in terms of x. And so, and I mean right now, so let's go back to this picture. This orange segment that has length d is clearly not the same distance as this little arc, this blue arc here. However, if we make our subinterval from xi minus 1 to xi really, really small, they're basically about the same, exactly the same. If we make it infinitesimally small interval, so we shrink this interval right here down. If we shrink that interval down and make it smaller, which is the idea of calculus, we can find the exact length. And so that's what we're going to do in order to find arc length. And we usually call that L. In order to find arc length, we're going to use calculus. We're going to take the limit as n approaches infinity of a Riemann sum going from I equals 1 to infinity of that quantity that we just found. So that's, again, that's delta x squared plus, now instead of delta yi, that's equivalent to f prime of x star times delta x squared. And since both of these expressions have delta x squared in them, we can factor that out. So if I do that, I can rewrite this. Limit as n approaches infinity, sum from I equals 1 to infinity, and we have the square root of delta x squared times the quantity 1 plus f prime of x star squared. And because the square root of delta x squared is just delta x, we can simplify this one more time. We can say this is the limit as n approaches infinity. We have our sum again. And then we've pulled out then the delta x, leaving inside the square root 1 plus f prime of x star squared. And here's where the calculus comes in. That means that instead of having this infinite, the limit of a infinite sum, we can just use an integral. And so it's going to be the integral from a to b, that's our interval, and it's going to be the integral of 1 plus f prime of x squared, and then the delta x, of course, becomes dx. And we're not going to go through it, but you could also show a similar development for how to find the arc length when our function is x is a function of y. And in that case, it's going to be the integral from, let's call it c to d of the square root of 1 plus g prime of y squared dy. So you can do it that way. There's two different ways that we could do these problems, depending on if your function is given as a function of x or a function of y. And so this is what we're going to use for arc length. You can pick either one. Let's look at an example. So again, at the top of the next page, you can see both of those formulas and when to use them. So in example 1, we have y given as a function of x. So if we look real quick at these two theorems, we're going to want to use theorem 2.4 because we have a graph of a function of x, and which means we need to find the derivative of that function. And I'm going to go ahead and rewrite this real quick. You can rewrite this as 1/16 x to the 4th plus 1/2, excuse me, 1/2 x to the minus 2. And this way it's a lot easier to use the power rule. So that means the derivative, y prime, is going to be 1/16 times 4x to the 3rd. We have plus 1/2. And using the power rule there, we have minus 2 times x to the minus 3. And just clean that up a little bit, that looks like 1/4 x to the 3rd minus 3. That's going to go to the bottom, so the 1/2 cancels with the negative 2. Those multiply together, and we get 1 over x to the 3rd. So our arc length formula is going to be the integral from 1 to 2, because remember it says our interval was from 1 to 2, so we're going to take the integral from 1 to 2 of the square root of 1 plus that derivative that we just found squared. So we have 1/4 x to the 3rd minus 1 over x to the 3rd squared dx. And we need to do a little bit of algebra there to multiply out that binomial. So let's go over here on the side, take a look at that algebra. So we have 1/4 x to the 3rd minus 1 over x to the 3rd squared. If we expand that, it looks like this. And then we want to multiply that out. And when we multiply it out, we're going to get 1/16 x to the 6th. And then minus 1/4. And then minus 1/4. And then plus 1 over x to the 6th. And simplifying things, we get 1/16 x to the 6th minus 1/2 plus 1 over x to the 6th. And if we go ahead and throw that back into our integral. This now becomes the integral from 1 to 2, the square root of 1 plus 1/16 x to the 6th minus 1/2 plus 1 over x to the 6th, the x. And we can combine the 1 and the minus 1/2, which makes this integral from 1 to 2 of 1 square root of 1/16 x to the 6th plus 1/2 plus 1 over x to the 6th. And then, as is the case with most problems like this, because of the square root, it would be nice if we were able to factor this, and it turns out that this does factor, and it factors into 1/4 x to the 3rd plus 1 over x to the 3rd squared, which works out nicely because the square root cancels the square, and this just becomes the integral from 1 to 2 of 1/4 x to the 3rd plus 1 over x to the 3rd, which, if we want to use the power rule on it, it probably makes sense to rewrite this as 1/4 x to the 3rd plus x to the -3. And then we go ahead and integrate. And when we do that, we get, you add 1 to the power, divide by that power, you get 1/16 x to the 4th, and then minus 1/2, then you get x to the -2, so that's x squared on the bottom. And then we're going to evaluate this from 1 to 2, which is going to give us 1 minus 1/8 when we plug in 2, and then when we plug in 1, we get 1/16 minus 1/2, and this simplifies down to 21 over 16. And this problem did not talk about units, but if it was an application type problem that did involve units, of course you could add some sort of units onto that answer. And that's how you find arc length. So let me know if you have any questions. That is going to conclude this video. Thank you.